Hello, friend. Some nights when the world grows still and the sky stretches endlessly above you, might find yourself wondering about the simplest things, like why the moon hangs so perfectly round in the darkness, or why every planet you've ever seen through a telescope wears the same gentle curve. There's something almost too quiet about it, isn't there? This roundness, this softness in the cosmos. Tonight, a single question drifts between the stars and your pillow. Why does everything with enough mass want to become a sphere, not a cube, not a pyramid, not some jagged, wild shape that screams individuality? Just round. It's the universe's most whispered secret, hiding in plain sight every time you glance at the sun, every time you hold a marble, every time a raindrop trembles at the edge of a leaf before it falls. Before we begin this quiet journey together, if you find comfort in these soft explorations of the cosmos, you might like to stay a while. You can gently tap the like button, subscribe if you'd like more stories told softly, and ring the little bell, not for noise, but so the next quiet night can find you again. We'll be here waiting in the stillness whenever you need us. Now, let's drift. Tonight, we'll float through the gentlest force in all of existence, the one that made stars, the one that shaped planets, the one that right now is holding you against the earth with a tenderness you've never noticed. Gravity doesn't shout. It doesn't demand. It simply pulls, quietly, endlessly, with a patience that has lasted 13 billion years. And in that pulling, it builds spheres. You don't need to understand everything. Just rest and let curiosity do the listening. There's a moment, isn't there? Just before sleep arrives, when your body feels heavier than it should. Your arms sink into the mattress. Your head presses deeper into the pillow. You're not falling exactly, but you're being held, pulled softly toward the center of something vast beneath you. That's gravity, doing what it has always done. It's the same force that convinced a cloud of dust 4.5 billion years ago to stop drifting and start gathering. The same whisper that shaped our planet from chaos into this blue sphere spinning through the void. The same architect that took the violent molten confusion of early Earth and smoothed it slowly, patiently into roundness. Scientists suggest that gravity might be the universe's quietest artist. It doesn't paint with color or light. It sculpts with time and mass, pulling everything inward equally from all directions. And when you pull equally from all sides, there's only one shape that makes sense. A sphere. Consider this right now as you lie here listening. 6 sextillion kilograms of rock water and air are being held together beneath you. That's 6 followed by 21 zeros. Every grain of sand, every drop of ocean, every breath of wind, all of it pressed together by gravity's constant embrace. The Earth pulls you down with a force of about 9.8 meters per second squared. That's just a number, of course, but it means that if you let go of something, anything, it will fall. Not because it wants to, but because the planet beneath it is whispering endlessly, "Come closer." And you do. Everything does. Research shows that this pull isn't unique to Earth. Every object with mass pulls on every other object with mass. Your coffee mug pulls on the moon. The moon pulls on your coffee mug. It's just that one of those pulls is so impossibly small, you'd need instruments more sensitive than anything we've built to measure it. But it's there. Isaac Newton, sitting in his mother's garden in 1666, watched an apple fall. He didn't get hit on the head. That's a story people made gentler for children. He simply watched it drop straight down and wondered why it fell toward the earth instead of sideways or up or at some strange angle. The answer he found changed everything. He realized that the same force pulling the apple downward was also holding the moon in orbit. The same invisible thread. Scientists suggest this was the first time anyone understood that the heavens and the earth obeyed the same rules. That gravity wasn't something that lived only on the ground pressing things into the soil. It lived everywhere. In stars, in planets, in the vast empty spaces between them. Newton gave us an equation, a simple one really. The force of gravity equals a constant multiplied by the masses of two objects divided by the square of the distance between them. It sounds cold when you say it like that, mathematical, but listen to what it really means. Every object whispers to every other object across the darkness. I'm here, they say. Come closer. And the closer you get, the louder that whisper becomes. Not in volume, but in pull, in inevitability. 250 years later, a man named Albert Einstein sat in a patent office in Switzerland and realized Newton had gotten something beautifully almost right. Gravity wasn't quite a force pulling things together. It was a curve. Imagine a bowling ball placed on a stretched bedsheet. The heavy ball sinks into the fabric, creating a depression, a well. Now imagine rolling a marble across that sheet. It doesn't travel in a straight line anymore. It curves, spiraling around the bowling ball, following the shape of the depression. That's what mass does to space itself. It bends it, curves it, and other objects moving through that curved space simply follow the contours, like water finding the lowest point in a landscape. Einstein called it space-time, 4 dimensions woven together, 3 of space, 1 of time, forming a fabric that could be stretched, compressed, twisted by the presence of mass. Some believe this might be the most elegant truth ever discovered. Gravity doesn't pull. It simply shows matter where to go. On May 29th, 1919, during a total solar eclipse, a British astronomer named Arthur Eddington traveled to the island of Principe off the coast of Africa. He pointed his telescope at stars near the sun's edge, stars that should have been hidden behind the sun's glare. But the moon had covered the sun, turning day into twilight, and those stars became visible. Except they weren't quite where they should have been. Their light had bent, curved around the sun's mass, exactly as Einstein predicted. The fabric of space itself had warped, and the starlight followed that warp. It seems as though the universe had confirmed in that moment that mass and space are dancers endlessly shaping each other. But here's what pulls us back to our question, the one that started this gentle drift. If gravity pulls equally from all directions, what shape must everything become? Think about it slowly, the way thoughts arrive just before sleep. If you're pulling inward from the north, and inward from the south, and inward from the east and west, and every direction in between, all with the same gentle insistence, what happens? You get a sphere. Not because the universe demands it, but because a sphere is the only shape that makes sense. It's the shape where every point on the surface is exactly the same distance from the center. The shape where gravity's pull is balanced, equal at rest. Some nights it helps to know that even chaos has a preference. Even randomness, given enough time and mass, will settle into roundness. A sphere is the universe's sigh of relief. It's the shape of least resistance, the form that requires the least energy to maintain. Nature doesn't force it. Nature simply finds it easier. Imagine trying to build a cube out of liquid. You'd need walls, containers, something to hold the corners rigid, but a drop of water in zero gravity. It becomes a perfect sphere without any effort at all. Surface tension pulls equally, and roundness emerges like breathing. Gravity does the same thing, but with mass instead of molecules. Scientists have found that once an object gathers enough matter, somewhere around 400 to 600 kilometers in diameter, for icy bodies, 600 to 1,000 for rocky ones, its own gravity becomes strong enough to overcome the structural strength of rock itself. Mountains collapse, valleys fill, jagged edges smooth. The object pulls itself into a sphere the way you might pull a blanket around yourself on a cold night. Not dramatically, just naturally. Right now beneath you, the Earth is doing exactly this. It's not a perfect sphere, of course. Nothing in the universe is perfect. But it's close, so close that if you shrank the Earth down to the size of a billiard ball, it would be smoother than any billiard ball ever made. The highest mountain, Everest, rises about 8.8 kilometers above sea level. The deepest trench, Mariana, plunges about 11 kilometers below. That sounds dramatic until you remember that the Earth's diameter is over 12,000 kilometers. Those variations, the mountains, the valleys, the wrinkles in the crust, they're barely noticeable. Bumps on something so vast. And still, gravity keeps pulling, keeps smoothing. Mountains erode. Sediment settles. The planet breathes slowly over millions of years, always trying to become more spherical, more balanced, more at rest. It seems as though even planets know the shape they're meant to become. Have you ever wondered why you feel heavier when you're tired? It's not gravity increasing. It's you finally noticing it. Your muscles stop fighting the pull. Your bones settle. You surrender to the planet beneath you, the same way matter surrenders to its own mass. That feeling, that heaviness just before sleep, is the same force that shaped worlds. Gravity is patient. It doesn't rush. It has been pulling for longer than time itself has meaning. Before, the Earth was solid when it was still a churning sea of molten rock, and metal gravity was already there, whispering, "Become round, become still, become whole." And the Earth listened. 4.5 billion years of listening. We live on the result of that ancient conversation between mass and space, between matter and the geometry it creates. Every step you take presses against a sphere. Every horizon you see curves ever so gently away from you. Every sunrise proves that you're standing on something round, spinning through an ocean of stars. Tonight, as you drift towards sleep, maybe you'll feel it differently. Not as weight, but as embrace. The planet holding you the way gravity has always held everything. Softly, endlessly, without exception. There's something deeply calming about inevitability, isn't there? Knowing that the universe has preferences, that chaos given time becomes order, that even in the vastness of space, there are rules gentle enough to create beauty. Spheres are one of those rules. They're the shape of moons and planets of stars and droplets of soap bubbles, catching light and distant galaxies too far to name. They're the shape gravity chooses when left alone with enough mass and enough time. And perhaps that's why we find them so soothing. Circles, spheres, roundness. They feel complete, whole, like something that is finished becoming, and now simply is. The ancient Greeks believed spheres were perfect because they had no beginning and no end. You could trace your finger around a circle forever, never finding where it started. Modern physics suggests they were closer to truth than they knew. A sphere is the geometry of equilibrium, of forces balanced, of time stretched into space, and space folded into itself. It's the shape of rest. And on a night like this, when the world grows quiet and your thoughts slow, their racing rest is all that matters. So let's continue this gentle drift together. We've barely begun to explore what gravity builds when given enough matter to work with. We've stood here on Earth feeling its pull, understanding why it became round. But there are other spheres waiting in the darkness, spheres made of gas that burn for billions of years, spheres so dense that a teaspoon of their matter would weigh as much as a mountain. Spheres that aren't made of matter at all, but of pure warped space, bending light itself into rings of gold. Gravity hasn't finished teaching us yet. In the next part of our journey, we'll drift back in time to the moments when humans first understood what holds the cosmos together. We'll walk through gardens where apples fall. We'll stand on beaches during eclipses that proved space itself could bend. We'll meet the minds that looked at the heavens and saw not gods, but geometry. The story of how we learned that gravity shapes spheres is also the story of how we learned to see the universe clearly. And that story is waiting just ahead in the quiet. The year was 1666, and England was dying. The bubonic plague swept through London like a dark tide, claiming thousands of lives each week. Universities closed. Streets emptied. A young Cambridge student named Isaac Newton, barely 23 years old, fled to his family's manor house in Woolsthorpe, Lincolnshire, to wait out the pestilence in the countryside. He had no idea those 18 months of isolation would change how we see the universe. In that quiet garden surrounded by apple trees his mother tended, Newton began to wonder about falling. Not the falling of empires or fortunes, but something simpler. Something that happened so constantly, so quietly, that most people never questioned it at all. Why did things fall down? It seems like such an obvious question now. But in 1666, nobody really knew. Some ancient philosophers thought heavy objects fell because they wanted to return to Earth. Others believed invisible hands pushed things downward. The prevailing wisdom suggested that celestial bodies, the moon, the planets, the stars, obeyed entirely different laws than earthly objects. Heaven was heaven. Earth was earth. Newton, watching apples drop in his mother's garden, suspected something else entirely. The story you've heard, the one where an apple bonked him on the head and sudden enlightenment arrived, never happened. That's a tale smoothed over by time, made simpler for children's books. The truth is quieter, more patient. Newton sat. He observed. He watched apples fall straight down, perpendicular to the ground, over and over again. Always down, never sideways, never hovering uncertainly, just down as if Earth itself were calling them home. And then he looked up at the moon. It hung there in the afternoon sky, pale and round, neither falling nor flying away, orbiting held in place by something invisible, something that had kept it circling Earth for longer than human memory could reach. What if Newton wondered the force pulling the apple down was the same force holding the moon up? What if there was no difference between heaven and earth at all? Research shows this might have been the single most important question anyone has ever asked. Because in that moment in that garden, Newton began to see the universe as one thing governed by one set of rules, instead of two separate realms, following separate laws. He called the force gravity, from the Latin gravitas, meaning weight or heaviness. But he didn't just name it. He measured it, quantified it, gave it an equation so precise we still use it today more than 300 years later. The force of gravity Newton discovered equals a constant, a number that never changes, multiplied by the mass of the first object, multiplied by the mass of the second object, divided by the square of the distance between their centers. Written simply, F equals G times M1 times M2 divided by R squared. It's just symbols on paper. But listen to what those symbols actually mean. Every object with mass pulls on every other object with mass. Your body pulls on the earth. The earth pulls on you. The moon pulls on the oceans, creating tides. The sun pulls on the planets, keeping them in their eternal dance. Even the book on your nightstand and the lamp beside your bed are pulling on each other, though with a force so incomprehensibly tiny, you'd never feel it. Scientists suggest that this might be the universe's most fundamental conversation. Every piece of matter everywhere constantly whispering to every other piece, "I'm here. Come closer." The strength of that whisper depends on two things: how massive the objects are and how far apart they sit. Double the mass, and you double the pull. But double the distance, and the pull becomes 4 times weaker. Double it again, and it's 16 times weaker. The relationship is exponential, which means that gravity falls off rapidly with distance, but never quite reaches zero. Right now, the Andromeda Galaxy, 2.5 million light-years away, is pulling on you. The force is unimaginably small, far too weak to measure with any instrument we've built, but it exists. You are connected through gravity to everything in the cosmos. Newton's equation worked beautifully. It predicted planetary orbits with stunning accuracy. It explained tides, falling objects, the shape of the Earth's bulge at the equator. It let astronomers discover Neptune in 1846 by noticing that Uranus's orbit wobbled, slightly tugged by an unseen neighbor. For 230 years, Newton's gravity was enough. But then came Albert Einstein. In 1905, while working as a patent clerk in Bern, Switzerland, Einstein published 4 papers that shook physics to its foundation. One of them introduced special relativity, the idea that space and time aren't separate fixed things, but are woven together into a single fabric that can stretch and compress depending on how fast you're moving. But even special relativity had a problem. It couldn't explain gravity. For 10 years, Einstein wrestled with the question. He called it the happiest thought of his life when in 1907 he imagined a man falling from a roof. During that fall, before hitting the ground, the man would feel weightless. He wouldn't feel gravity pulling him down. From his perspective, he'd be floating even as the ground rushed up to meet him. It seems as though gravity and acceleration might be the same thing experienced from different perspectives. This led Einstein to a radical idea. What if gravity isn't a force at all? What if mass doesn't pull on other mass, but instead warps the very fabric of space and time around it? Imagine the universe as a vast, stretched bedsheet, perfectly flat when empty. Now place a bowling ball in the center. The sheet sags, creating a depression, a valley. The heavier the ball, the deeper the valley. Now roll a marble across that sheet. It doesn't travel in a straight line anymore. It curves, spiraling around the bowling ball, following the contours of the warped fabric. The marble isn't being pulled by a force. It's simply following the straightest possible path through curved space. What looks like pulling is actually geometry, the shape of space-time itself. Einstein called this general relativity, and he published it in 1915 in the middle of World War I, while Europe tore itself apart. The mathematics were beautiful, elegant, and utterly strange. His equations showed that massive objects don't just sit in space, they reshape it. The sun doesn't pull Earth with invisible strings. The sun creates a depression in space-time, and Earth rolls endlessly around the edge of that depression, like a coin spiraling in a charity funnel. Except the coin never falls in, and the spiral never ends. Some believe Einstein's theory might be the closest humans have ever come to seeing the universe's source code, but theories need proof. And in 1915, during wartime, proof seemed impossible. Then came the eclipse. On May 29, 1919, the moon passed directly between Earth and the sun, casting a shadow across the Atlantic Ocean. A British astronomer named Arthur Eddington, along with his colleague Andrew Crommelin, organized 2 expeditions, one to the island of Principe off the coast of West Africa, the other to Sobral in Brazil. Their mission photographed stars near the sun's edge during totality, when the moon blocked the sun's overwhelming light. According to Newton, starlight should travel in perfectly straight lines. The sun's gravity might pull on the light infinitesimally, but not enough to measure. According to Einstein, the sun's mass should warp space-time enough to bend that starlight noticeably, shifting the star's apparent positions. Eddington needed clear skies and steady hands. The eclipse would last only a few minutes. One chance, one moment to test whether space-time could actually curve. On Principe, clouds threatened to ruin everything. But just as totality began, a gap opened in the overcast. Eddington captured his photographs, measuring star positions with painstaking care. When he developed the plates and compared them to photographs of the same stars taken months earlier, when the sun wasn't nearby, the results were unmistakable. The stars had moved. Not much, just 1.61 arcseconds, about the width of a quarter viewed from 2 miles away. But they had moved, shifted exactly as Einstein predicted. Light itself had bent around the sun's mass. Research shows that this single observation transformed Einstein from an obscure physicist into a global celebrity overnight. Newspapers around the world announced, "Lights all askew in the heavens." The New York Times declared it a revolution in science. And it was. Because if space-time could bend, if mass could warp the very fabric of reality, then everything we thought we understood about the universe needed rethinking. Gravity wasn't a force reaching across emptiness to pull things together. Gravity was the shape of space itself, curved and folded by the presence of mass-guiding objects along paths that only looked like pulling. Einstein once described it this way: space tells matter how to move. Matter tells space how to curve. It's poetry disguised as physics. Here's what that means for our question about spheres. If mass warps space-time, and if that warping happens equally in all directions around a massive object, then the natural result is a symmetrical depression, a well that looks the same no matter which direction you approach it from. A sphere. Not because the universe demands it, but because symmetry is what happens when forces balance perfectly. Think about water finding its level in a glass. You don't have to tell it where to go. You don't have to sculpt it into flatness. Gravity and pressure balance themselves, and flatness emerges naturally. The same thing happens in 3 dimensions with mass. Give something enough matter, enough self-gravity, and it will pull itself into the shape where every point on the surface is equidistant from the center. That shape is a sphere. Scientists suggest that this might be why spheres feel so fundamental, so right. They're not imposed from outside. There, what matter becomes when left alone with itself, when gravity's democracy, pulling equally from all sides, has time to vote. But here's something Newton and Einstein both understood. Gravity is weak. Impossibly, almost laughably weak. The electromagnetic force that holds atoms together is about 10 to the 36th power stronger than gravity. That's a 1 followed by 36 zeros. If you've ever pulled a paperclip off a table with a tiny magnet, you've watched a force the size of a marble overpower the gravitational pull of the entire Earth. Yet gravity wins in the end. Why? Because gravity only pulls. It never pushes. It never repels. And it never turns off. Electromagnetic forces balance out. Positive and negative charges cancel each other. The strong nuclear force only works at incredibly tiny distances. But gravity accumulates. Add more mass, get more pull. Add even more mass, get even more pull. Given enough matter and enough time, gravity becomes unstoppable. That's how stars form, how planets coalesce, how galaxies spiral into being. And that's how spheres emerge from chaos. Newton gave us the mathematics of that pull. Einstein gave us the geometry. Together, they showed us that the universe isn't held together by invisible ropes or divine intervention, but by the simple, elegant fact that mass and space are in constant conversation, reshaping each other, finding balance. It seems as though understanding gravity meant learning to see what isn't there, the invisible architecture that holds everything together. Have you ever noticed how satisfying it feels to watch water droplets bead up on a waxy surface, each one perfectly round, catching light, trembling with surface tension? That's not gravity exactly. That's molecular forces pulling the water into minimum surface area. But it's the same principle. Nature doesn't waste energy maintaining complicated shapes when a simple one will do. A sphere requires the least surface area for a given volume. It's efficient, economical, inevitable. Gravity operates on the same economy, but with mass instead of molecules. From Newton's garden to Einstein's equations, from falling apples to bending light, the story of gravity is also the story of humans learning to see patterns in places we didn't know to look, learning that heaven and earth speak the same language, learning that what appears solid is actually geometry, and what appears empty is actually curved. We began this part of our journey with a plague and an apple. We end it with eclipses and equations, with the understanding that gravity doesn't pull things down, It shows them where to go through the curved landscape of space-time itself. But understanding the force is only the beginning. Now we need to understand the shape it creates. We need to ask why spheres aren't just common in the universe, but inevitable. Why every structure, massive enough to feel its own gravity, will eventually become round. The mathematics of that roundness, the elegant geometry of minimum energy, waits just ahead in the stillness. There's a question that sounds simple until you really think about it. Why is a sphere the most common shape in the universe? Not spirals, though galaxies love those. Not cubes, though. Crystals build themselves with rigid angles. Not pyramids or cylinders, or any of the infinite other geometries that mathematics allows. Just spheres. Everywhere. In every direction you look. The answer hides in something quieter than gravity itself. Something that governs not just planets and stars, but soap bubbles in your sink. Raindrops on windows, the way oil beads up in water. It's a principle so fundamental that nature uses it everywhere, from the smallest droplet to the largest star. The universe, it seems, is lazy. Not in a careless way, but in the most elegant way possible. Given any choice, nature will always choose the path that requires the least energy, the least effort, the least work to maintain. And in 3 dimensions, when you need to hold a given volume of matter together, there's only one shape that requires minimum surface area: a sphere. Before we drift deeper into this quiet mathematics, let me share something with you. If these gentle explorations into the cosmos bring you peace, you might want to stay connected. The like button is there if this resonates with you, and subscribing means we can continue these soft journeys together. The bell icon. If you choose it, we'll let the next story find you when you need it most. We'll be here in the stillness waiting. Now let's begin where the mathematics becomes almost touchable. Imagine you're holding a balloon, not inflated yet, just limp rubber in your hands. As you begin to blow air into it, something remarkable happens. The balloon doesn't become a cube, or a pyramid, or some wild irregular shape. It becomes round. You didn't tell it to. You didn't sculpt it. Roundness simply emerged. Scientists suggest this happens because the rubber membrane is trying to contain the air pressure inside while using the least amount of material possible. And the shape that encloses the maximum volume with the minimum surface area is always, inevitably, a sphere. This is an opinion, it's geometry. Research shows that for any given volume, a sphere has about 20% less surface area than a cube of the same volume. Less surface means less material needed, less energy required to maintain the shape, less resistance to whatever forces are acting on it. Nature notices that 20%. Nature always notices efficiency. Watch what happens when you let a drop of water fall from a faucet. In that brief moment of free fall before it hits the sink, the droplet becomes almost perfectly spherical, not because water wants to be round in some mystical sense, but because surface tension, the cohesive force between water molecules, pulls the surface inward from all directions, equally. The result: minimum surface area, maximum efficiency, a sphere. The same thing happens in space, but with gravity instead of surface tension. When you have enough mass gathered in one place, gravity pulls inward from all directions, not preferentially from the top or bottom, not more strongly from the sides. Equally, democratically, from everywhere at once. And when you pull equally from everywhere, you get a shape where every point on the surface is the same distance from the center. That's the definition of a sphere. Here's where it becomes beautiful. A sphere isn't just efficient in terms of surface area. It's also the shape of equilibrium, the geometry of balance. Every point on a spherical surface experiences the same gravitational pull toward the center. No point is favored. No direction is privileged. It's gravity's way of being fair. Scientists in the 18th century understood this intuitively. A French mathematician named Pierre-Louis Maupertuis proposed what he called the principle of least action in 1744. It suggested that nature always chooses the path that minimizes a certain quantity, action, a combination of energy and time. Others refined this idea, discovered that it applied not just to motion, but to shape, to structure, to the way matter arranges itself when forces compete for dominance. In the case of celestial bodies, two forces compete: gravity, pulling inward, trying to compress everything into the smallest possible space, and pressure, pushing outward, resisting that compression. When these forces balance, when the inward pull equals the outward push at every point, you achieve what physicists call hydrostatic equilibrium. And hydrostatic equilibrium in 3 dimensions always yields a sphere. Think about a balloon again, but this time imagine it's made of rock and metal instead of rubber, and instead of air pressure inside, you have the pressure of hot, compressed matter. Gravity squeezes inward. Pressure pushes outward. Where they meet, where they balance, a surface forms. If gravity is stronger at one point than another, that point will collapse further inward until the forces equalize. If pressure is higher, somewhere that region will bulge outward until balance returns. The system self-corrects, constantly adjusting, until every point on the surface exists in perfect equilibrium with every other point. The only shape that satisfies this requirement is a sphere. Research shows that this principle applies whether you're talking about a planet made of rock, a star made of plasma, or a droplet made of water. The scale changes, the materials change, but the geometry remains constant. Spheres are the universe's favorite answer to the question, how do I hold this together with the least effort? Now here's something that surprises most people. The International Astronomical Union in August 2006 had to redefine what counts as a planet. They discovered so many objects in the outer solar system, Eris Makemake Haumea, and others, that the old definition no longer worked. One of the key criteria they established was this: a planet must have sufficient mass for its self-gravity to overcome rigid body forces, thereby achieving hydrostatic equilibrium. In simpler words, it must be round. Not perfectly round. Nothing in the universe is perfect, but round enough that gravity has won the war against the structural strength of rock and ice. This threshold exists at different masses depending on what the object is made of. Icy bodies can achieve roundness at smaller sizes because ice is weaker than rock, more easily deformed by gravity's patient pull. Rocky bodies need more mass, more self-gravity, before they can squeeze themselves into spheres. Scientists suggest the threshold sits around 400 to 600 kilometers in diameter for icy objects and 600 to 1,000 kilometers for rocky ones. Below that size, The object's material strength can resist gravity. Mountains can stand tall. Valleys can remain deep. Irregular shapes persist because the rock is strong enough to hold itself up against its own weight. Above that threshold, rock becomes putty in gravity's hands. Consider Saturn's moon, Mimas. It measures about 396 kilometers across, just barely large enough to achieve roundness. Look at photographs of Mimas, and you'll see something haunting a nearly perfect sphere, but covered in craters so deep they suggest this moon only recently finished pulling itself together. One crater, Herschel, spans a third of Mimas's diameter, a giant eye staring out into the void. The impact that created that crater nearly shattered Mimas entirely, but gravity held, pulled the pieces back together, maintained that hard-won roundness. Now compare Mimas to an asteroid like Ida, which measures about 58 kilometers long. Ida looks like a potato, lumpy and irregular, because it doesn't have enough mass for its gravity to overcome the structural strength of rock. It can afford to be jagged. Its gravity is too weak to smooth itself. The mathematics here reveals something profound. Shape isn't decorative in the universe. Shape is a consequence of forces, a record of battles won and lost between gravity's compression and matter's resistance. Spheres are what happen when gravity wins decisively. But there's another layer to this, something even more fundamental. Remember that surface area and volume relationship. A sphere minimizes surface area for a given volume, but it also maximizes something else, entropy. Entropy is often described as disorder, but that's not quite right. It's better understood as the number of ways a system can arrange itself while still looking the same from the outside. A sphere has infinite rotational symmetry. You can turn it any direction, any angle, and it looks identical. That means there are countless ways the internal structure can organize itself while maintaining that external spherical shape. Nature loves options. Research in thermodynamics shows that systems naturally evolve toward states of maximum entropy, maximum possibility. And for a gravitationally bound object, that state is spherical. It's not just the easiest shape, it's the shape with the most freedom. Think about ocean waves for a moment. When a wave breaks on shore, it dissipates energy. All that motion, that height, that power it spreads out flattens, becomes still. The water doesn't disappear. It just finds a lower energy state, a configuration that requires less work to maintain. Gravity does the same thing with matter, but over millions of years, instead of seconds. Mountains are waves that haven't finished breaking yet. Give them time. Give them enough time, and they'll erode. Settle spread out. The material won't vanish. It'll just find a shape that requires less energy to hold. A sphere. Some believe this might be why spheres feel so calming to look at. They represent resolution, completion, forces that have finished fighting and found peace in geometry. Here's a question worth sitting with. Have you ever tried to balance a pencil on its tip? It's nearly impossible. The slightest vibration, the tiniest breath of air, and it topples. That's because a pencil standing upright is in unstable equilibrium. Any deviation from perfect vertical gets amplified, and the system collapses into a lower energy state, the pencil lying flat. Now imagine trying to push a ball off balance. You can roll it, sure, but you can't tip it over, because there's no edge to tip from no direction that's more stable than any other. A sphere exists in the deepest possible equilibrium, the configuration that resists change most effectively. That's why planets don't need constant adjustment to maintain their shape eye. Once they've achieved roundness, they're settled into a geometric valley so deep that only catastrophic forces can disturb them. Scientists use equations to describe this mathematics that would fill chalkboards. But the principle underneath is almost childishly simple. Things fall to the lowest point they can reach and stop there. For geometry, for shape itself, that lowest point is a sphere. The ancient Greeks understood this intuitively, though they couldn't prove it mathematically. Plato considered spheres the most perfect form, the shape closest to divine. Aristotle argued that celestial bodies must be spherical, because that's the only shape worthy of the heavens. They were reaching for a truth they could feel, but not calculate. It took 2,000 more years until the calculus of variations was developed in the 17th and 18th centuries, before anyone could prove mathematically why spheres minimize surface area. Mathematicians like Leonhard Euler and Joseph Louis Lagrange developed techniques to find optimal shapes, curves that maximize or minimize certain quantities. And every time they asked, what shape encloses this volume with minimum surface? The answer came back the same: a sphere. It seems as though the universe might be less mystical than the Greeks imagined, but no less beautiful. The perfection they sensed wasn't divine preference. It was mathematics, working itself out through gravity and time. Here's something to carry with you as you drift towards sleep. Tonight, you are right now resting on the surface of a sphere that took 4.5 billion years to smooth itself. Every mountain beneath you, every ocean, every grain of sand exists because gravity spent eons pulling matter into the most efficient arrangement possible. The earth beneath you isn't round because someone designed it that way. It's round because roundness is what happens when you leave matter alone long enough with its own gravity. That's the deepest kind of inevitability. Not forced, not imposed, just allowed to become. We've explored why spheres emerge from the mathematics of minimum energy. We've seen how nature's laziness creates cosmic perfection. But understanding the principle is one thing. Watching it happen in real time across billions of years as a planet actually becomes round, that's another journey entirely. And Earth's own transformation from chaos to sphere is waiting to unfold in the next part of our drift through the darkness. 4.5 billion years ago, there was no ground beneath your feet, no continents, no oceans, no sky to look up toward, just a churning disk of dust and gas spiraling around a newborn star, colliding and clumping and building itself into something that would one day become home. The Earth you're resting on right now didn't arrive fully formed. It was born from violence, from countless impacts, from a chaos so complete that the entire planet existed as an ocean of molten rock, glowing orange in the darkness, spinning wildly through space. And somehow, over unimaginable stretches of time, that chaos settled, cooled, rounded itself into the gentle sphere that now holds you while you listen. The question is how? How does a planet learn to be round? If you find peace in these quiet wanderings through deep time, you might want to leave a small mark, a like, to let me know you're here, a subscription. If you'd like to return to these stories, a bell, if you want the next journey to find you. We're building something together in this stillness, you and I. One breath, one star, one sphere at a time. Now let's drift back to the beginning. In the early solar system, around 4.6 billion years ago, our sun had just ignited. The leftover material from its formation, dust ice rock metals, circled in a vast disk called the solar nebula. Within that disk, tiny particles collided, stuck together, grew. Scientists call this process accretion, from the Latin meaning to grow. It sounds gentle, almost peaceful, but it was anything but. Imagine two rocks, the size of houses, traveling at thousands of kilometers per hour, slamming into each other with enough force to vaporize metal. Most of the time, they'd shatter fragment, scatter back into the disk. But sometimes, just sometimes, they'd stick. Their mutual gravity, weak but persistent, would hold the pieces together. Do this billions of times, over millions of years, and you start to build something larger. Research shows that Earth likely grew through three distinct phases. First came the planetesimals, objects ranging from 1 to 100 kilometers across, like the asteroids we still see today. These formed relatively quickly, within just 100,000 years or so, as dust grains stuck together through static electricity in gentle collisions. Then came the planetary embryos, bodies about the size of Mars, forming over 1 to 10 million years through increasingly violent impacts. Dozens of these embryos orbited the young sun, their paths crossing and recrossing an orbital demolition derby, playing out in slow motion. And finally, in the most dramatic phase, these embryos collided with each other in what scientists call giant impacts. When two Mars-sized bodies hit each other at cosmic velocities, the energy released is beyond comprehension. The entire surface melts, vaporizes, becomes a glowing sea of liquid rock thousands of kilometers deep. Earth experienced hundreds of these impacts in its first 100 million years. The largest one, about 4.5 billion years ago, involved a Mars-sized body that astronomers call Theia. The collision was so violent that it vaporized both Theia and a significant portion of Earth's outer layers. The debris launched into orbit eventually coalesced into our moon. But here's what matters for our story. After each impact, after the violence subsided, gravity began its patient work of restoration. The molten rock didn't stay chaotic. It couldn't. Gravity pulled inward from all directions, and the densest materials sank toward the center, while lighter materials floated upward. This process is called differentiation, and it's how Earth developed its layered structure, iron and nickel core at the center rocky mantle, in between lighter crust on top. And as differentiation happened, something else occurred. Almost automatically, the planet began to round itself. Think about honey settling in a jar. At first, when you pour it in, there might be bubbles, irregularities, uneven surfaces. But given time, gravity smooths it all out. The honey finds its level, becomes flat on top, because that's the lowest energy configuration. Earth did the same thing, but in 3 dimensions instead of 2. Some believe this might have happened surprisingly quickly. Computer models suggest that a completely molten Earth spinning in space would achieve hydrostatic equilibrium roundness in just a few thousand years. That's instantaneous on geological timescales. But there's a complication. A beautiful one, actually. Earth isn't a perfect sphere. It never was, and it never will be. The planet bulges at the equator and flattens slightly at the poles, creating a shape that mathematicians call an oblate spheroid. The difference is subtle, but measurable. Earth's diameter at the equator is 12,756 kilometers, while the diameter from pole to pole is only 12,714 kilometers. That's a 42-kilometer difference. Why? Because Earth spins. Right now, at this very moment, the surface at the equator is moving at about 1,670 kilometers per hour, faster than the speed of sound. That rotation creates centrifugal force, an outward push that works against gravity's inward pull, causing the equator to bulge slightly. Scientists have measured this precisely. The centrifugal force at the equator reduces your effective weight by about 0.5% compared to what you'd weigh at the poles. Not much, but enough to reshape the entire planet over geological time. Research shows this same effect happens on every rotating body in the solar system. Jupiter spinning once every 10 hours bulges so dramatically that its equatorial diameter is nearly 10% larger than its polar diameter. Saturn, even faster, shows an even more pronounced bulge. Earth, rotating once every 24 hours, sits somewhere in between, round enough to be called spherical, but not perfectly so. Here's something that surprises almost everyone who learns it. Mount Everest, at 8,849 meters above sea level, is the highest point on Earth, but it's not the farthest point from Earth's center. That distinction belongs to Mount Chimborazo in Ecuador. Chimborazo rises only 6,263 meters above sea level, more than 2.5 kilometers shorter than Everest. But because it sits almost exactly on the equator, where Earth's bulge is greatest, its summit is actually 2,168 meters, farther from Earth's center than Everest's peak. If you stood on top of Chimborazo, you'd be standing on the point of Earth's surface that extends farthest into space. It seems as though even our definitions of height and distance depend on understanding Earth's shape, its subtle deviation from perfect roundness. But even this oblate spheroid shape isn't stable. Earth is constantly, imperceptibly becoming more spherical. How through plate tectonics? The crust beneath your feet isn't solid and unchanging. It's broken into massive plates that drift across the semi-molten mantle below, moving at about the same rate your fingernails grow a few centimeters per year. Where plates collide, mountains rise. Where they pull apart, ocean floors spread. Volcanoes erupt. Earthquakes shake. And through all this activity, Earth is healing itself, smoothing out irregularities, redistributing mass. Mountains, those dramatic exceptions to roundness, are temporary features on geological timescales. The Himalayas, Earth's youngest and tallest mountain range, began forming about 50 million years ago when the Indian plate collided with the Eurasian plate. They're still rising today, pushed upward by ongoing collision. But they're also eroding. Wind and water and ice wear them down grain by grain. Research shows the Himalayas erode at about 1 millimeter per year, slow by human standards, but fast enough that in a few tens of millions of years, they'll be mere hills. And where does that eroded material go? It washes into rivers, flows to the oceans, settles on the seafloor, eventually gets pulled back into the mantle through subduction zones and redistributed across the planet. Gravity. Always. Gravity pulling high places down and filling low places in trying endlessly to achieve perfect balance. Scientists suggest that if Earth's plate tectonics suddenly stopped, if all geological activity ceased, erosion alone would level the continents in about 250 million years. The mountains would wear away. The ocean basins would fill with sediment. Earth would become a perfectly smooth sphere covered by a global ocean about 2.5 kilometers deep. Of course, plate tectonics won't stop. The planet's interior remains hot, driven by radioactive decay and the residual heat from Earth's formation. But the thought experiment reveals something profound, left alone, without internal heat-driving geological activity. Gravity would inevitably create a perfect sphere. That's Earth's destiny, billions of years from now. Perfect roundness, perfect stillness. But there's another force reshaping Earth's sphere right now, one so gentle you've never consciously noticed it, the moon's tidal pull. Every day, twice a day, the oceans rise and fall. The solid Earth rises and falls too, though only by about 30 centimeters too small to feel, but large enough to measure with precise instruments. This rhythmic flexing dissipates energy, converting Earth's rotational momentum into heat through friction. The result, Earth's rotation is slowing down. Research shows that days are getting longer by about 1.7 milliseconds per century. It doesn't sound like much, but over geological time, it adds up. When Earth first formed, a day lasted only about 6 hours. When dinosaurs walked, the continents, a day was closer to 23 hours. Millions of years from now, Earth's day will be 25 hours, then 26, slowly approaching 27. And as Earth slows, something fascinating happens. The equatorial bulge decreases. Centrifugal force weakens. The planet becomes slightly more spherical. It's happening so slowly that no human will ever notice. But Earth notices. Gravity notices. The shape adjusts imperceptibly year by year, millennium by millennium. Some believe this might be the most remarkable thing about planetary roundness. It's not a state that's achieved and then frozen. It's a dynamic equilibrium, constantly adjusting to changing conditions, always seeking balance. Consider what this means for the ground beneath you. The atoms in the rock below the minerals and metals and molecules, they're all being pulled toward Earth's center, with precisely the same acceleration, 9.8 meters per second, squared, modified slightly by rotation and altitude. But they can't fall any farther because they're supported by the atoms below them, which are supported by atoms below them, all the way down to the planet's core. Every layer of Earth's interior exists in a state of compression, squeezed by the weight of everything above it. At the core, about 6,000 kilometers down, the pressure reaches 3.6 million times atmospheric pressure at Earth's surface. Iron atoms are packed so tightly that the material behaves unlike anything we can create in laboratories. It's solid, despite temperatures exceeding 5,000 degrees Celsius, held rigid by the sheer weight of the planet above it. And yet, even under that crushing pressure, the core maintains its spherical shape because a sphere is still the only geometry that can distribute that pressure equally in all directions. Scientists in the 17th century understood this principle before they understood its deeper causes. In 1687, the same year Newton published his law of gravitation, he also calculated that Earth must be an oblate spheroid based on the planet's rotation. He did this through pure mathematics, never leaving England, never seeing the planet from space. 50 years later, French expeditions to Lapland and Peru measured the length of a degree of latitude at different locations, confirming Newton's prediction. Earth really was slightly flattened at the poles. It seems as though we learned Earth's true shape by measuring it from the inside, by walking its surface with chains and angles and careful observations long before we could photograph it from above. The first humans to actually see Earth's roundness with their own eyes were the astronauts of Apollo 8 in December 1968. They orbited the moon and looked back toward home, seeing for the first time what billions of years of gravity had sculpted. Astronaut William Anders described it as a grand oasis in the big vastness of space. Astronaut Jim Lovell said simply, "The Earth looks so beautiful from here." And it was round. Perfectly, obviously, undeniably round. But even then, with cameras and instruments and human eyes confirming what mathematics had long predicted, some couldn't accept it. Flat Earth theories persist even now in the age of satellites and GPS, because sometimes the mind resists what the eye has never directly seen. Here's what's strange about that resistance. You don't need to go to space to know Earth is round. You can watch ships disappear, hull first, over the horizon. You can measure how shadows change length at different latitudes on the same day. You can observe lunar eclipses and see Earth's curved shadow on the moon's surface. Ancient Greek astronomers did exactly this more than 2,000 years ago. Eratosthenes, working in Alexandria around 240 BCE, calculated Earth's circumference to within 98% accuracy using nothing but shadows and geometry. He noticed that at noon on the summer solstice, the sun shone directly down a well in Cyane, casting no shadow. On the same day in Alexandria, about 800 kilometers north, a vertical stick cast a shadow at an angle of about 7 degrees. If Earth were flat, the shadow angles would be identical. But if Earth curved, the angles would differ. And from that difference, using basic geometry, Eratosthenes calculated the planet's circumference. He got 40,000 kilometers. The actual value is 40,075 kilometers. Not bad for someone working with sticks and shadows 2 millennia ago. It seems as though understanding Earth's shape has always been within human reach. We just needed to look carefully, measure precisely, and trust what the evidence revealed. The planet beneath you has been on a long journey from chaos to order, from violence to stability. It started as debris and collisions passed through an age of molten seas and giant impacts, and gradually settled into the gentle sphere you rest upon now. And that settling isn't finished. Won't ever be finished, really, as long as Earth continues spinning, as long as the moon continues raising tides, as long as the core continues radiating heat. Roundness isn't a destination. It's a process. An endless conversation between gravity and matter, between force and shape. But Earth is just one example, one voice in a much larger chorus. Beyond our atmosphere, other worlds have followed their own paths to roundness shaped by different masses, different compositions, different histories. The sun burns at the center of it all. Planets circle in their orbits, and moons drift through the darkness. Each one, a sphere in its own right. Each one, proof that gravity's patient architecture extends far beyond our home. That cosmic sculpture gallery awaits us in the stillness ahead. If you could stand outside the solar system and look back toward the sun, you'd see something that might surprise you. Not 8 separate worlds going their own way, not chaos or randomness, but a family portrait of spheres, each one hanging in the darkness like a pearl on an invisible string, each one testimony to the same patient force that shaped Earth. Mercury, Venus, Mars, Jupiter, Saturn, Uranus, Neptune, all round, every single one. Even the sun itself, that massive furnace at the center, burning so bright it hurts to look at, perfectly spherical, held together by its own immense gravity, a ball of plasma 99 times more massive than everything else in the solar system combined. It's almost too orderly, isn't it? Too precise. As if someone designed it this way. But no one did. These spheres emerged from nothing but dust time and the gentle insistence of gravity. Before we drift among these worlds, let me offer you something. If these quiet journeys through space bring you a sense of wonder, of peace, you're welcome to leave a gentle mark. A like to say, you were here. A subscription. To walk this path again. A bell. To let the next story find you when the night grows still. We're explorers together in this vast darkness, discovering what gravity built while the universe wasn't watching. Now let's return to the beginning, to where it all started. 4.6 billion years ago, there was no sun, no planets, no solar system at all. Just a vast cloud of gas and dust drifting through the Milky Way, unremarkable among billions of similar clouds, slowly rotating slowly, contracting under its own feeble gravity. Scientists call this the solar nebula. It stretched for light years in every direction, composed mostly of hydrogen and helium, left over from the Big Bang, mixed with heavier elements forged inside ancient stars that had lived and died before our sun was born. Something disturbed that cloud. Perhaps a nearby supernova sent shockwaves rippling through the nebula. Perhaps it simply reached a critical density where gravity could no longer be resisted. Either way, the cloud began to collapse, and as it collapsed, it spun faster. Conservation of angular momentum. The same principle that makes ice skaters spin faster when they pull their arms in. The nebula flattened into a disk with most of the mass falling toward the center, growing denser, hotter, more compressed. Research shows that within just 100,000 years, the blink of an eye on cosmic scales, the center of that disk grew hot enough and dense enough for nuclear fusion to ignite. The sun was born. Not all at once. Not with a dramatic explosion. Just a gradual brightening as hydrogen atoms in the core began fusing into helium, releasing energy in the form of light and heat. At first, the newborn sun was only about 70% as bright as it is now, surrounded by a disk of leftover material that would eventually become the planets. But here's what matters. From the very first moment fusion began, the sun became a sphere. It couldn't be anything else. With a mass equal to 330,000 Earths, the sun's gravity pulls inward with such force that the entire star exists in perfect hydrostatic equilibrium, the outward pressure from nuclear fusion exactly balancing the inward crush of gravity at every point. The result is a sphere so nearly perfect that its equatorial and polar diameters differ by only 10 kilometers out of almost 1.4 million kilometers total. That's a variation of less than 0.001%. If you could shrink the sun down to the size of a beach ball, it would be more perfectly round than any beach ball ever manufactured. Some believe this near-perfect sphericity tells us something profound about the balance inside stars. The sun isn't solid, it's plasma, a fourth state of matter, where electrons have been stripped from atoms by intense heat, creating a soup of charged particles. The plasma turns convex, rises and falls in massive currents. And yet, despite all that turbulence, despite the violence of fusion at the core and the roiling of magnetic fields that create sunspots and solar flares, the overall shape remains unwaveringly spherical. Because gravity doesn't care about turbulence. It cares about mass, and the sun has enough mass to hold itself together against any internal disruption. Scientists have calculated that the sun contains 99.86% of all the mass in the solar system. Jupiter, the largest planet, accounts for most of the remaining 0.14%. Everything else, all the other planets' moons, asteroids, comets, dust, and gas, amounts to barely a rounding error. The sun dominates, and in that dominance, it shapes not just itself, but the space around it, creating the gravitational architecture that keeps planets in their orbits, that determines their paths through the void. But let's drift outward now, toward those planets, those smaller spheres orbiting the greater one. Mercury, closest to the sun, completes one orbit every 88 Earth days. It's small, only slightly larger than our moon, with a surface scarred by billions of years of meteorite impacts. Some craters date back 4 billion years to the era of heavy bombardment, when the inner solar system was a shooting gallery of debris. And yet, despite being battered, despite having surface features that rise and fall by several kilometers, Mercury is spherical. Its gravity, though only 38% as strong as Earth's, is still sufficient to pull the planet into hydrostatic equilibrium. Research shows Mercury has a massive iron core that makes up about 61% of the planet's volume, the largest proportion of any planet in the solar system. That dense core generates enough gravitational pull to compress the overlying rock, smoothing out irregularities, maintaining roundness despite the violence written across its surface. Scientists suggest that if you could stand on Mercury's cratered plains and look up, you'd see the sun 3 times larger than it appears from Earth, burning with an intensity that would melt lead. The day side reaches 430 degrees Celsius. The night side plunges to minus 180 degrees. Extreme temperature swings, relentless radiation, ancient craters preserving 4 billion years of history, and through it all, spherical. Venus next outward presents a different mystery. It's the most perfectly spherical planet in the solar system, with surface variations of less than 1 kilometer from a perfect sphere. No mountains rise dramatically. No trenches plunge deeply. The surface is remarkably smooth, remarkably even. Why? Because about 500 million years ago, something catastrophic happened. The entire surface of Venus melted, resurfaced itself with volcanic flows, and froze into its current state. Whatever mountains existed before whatever valleys or craters they were erased, covered over with fresh lava that spread evenly across the planet. Gravity took advantage of that molten state to pull Venus into its most spherical form, and the planet has remained largely unchanged since then. Frozen not in ice, but in extreme roundness. Scientists have found fewer than 1,000 craters on Venus's surface compared to hundreds of thousands on Mercury and Mars. The surface is young, geologically speaking, reset, smoothed, a sphere so perfect it seems almost artificial. But Venus hides violence beneath that smooth facade. The atmosphere is pure poison carbon dioxide, thick enough to crush submarines' clouds of sulfuric acid surface pressure 90 times greater than Earth's. The greenhouse effect has run wild, creating a hell world where temperatures reach 470 degrees Celsius. And still round. Gravity doesn't judge, doesn't care about hospitality. It simply shapes. Mars' fourth from the Sun tells yet another story. It's smaller than Earth, only about half the diameter, which means its gravity is weaker. Only 38% of Earth's surface gravity. You might think that would prevent Mars from achieving good sphericity. But Mars is round enough. Not perfectly round. It has an equatorial bulge from rotation, just like Earth, but round enough to qualify as a planet under the International Astronomical Union's definition. What's remarkable about Mars is what it maintains. Despite weak gravity, Olympus Mons, the largest volcano in the solar system. It rises 25 kilometers above Mars's reference elevation, nearly 3 times the height of Mount Everest, and spreads 600 kilometers across at its base. On Earth, a mountain that large couldn't exist. Our stronger gravity would cause it to collapse under its own weight, the rock flowing like putty over geological time. But Mars's weaker gravity allows Olympus Mons to stand a monument to what's possible when gravitational compression is reduced. And yet, even Olympus Mons barely affects Mars's overall sphericity. 25 kilometers sounds enormous, but Mars's diameter is 6,800 kilometers. That mountain represents less than 0.4% deviation from roundness. Some believe this reveals something essential. Even dramatic surface features are trivial compared to planetary scale. Gravity, working across thousands of kilometers, smooths everything into curves. Beyond Mars lies the asteroid belt, and beyond that, the true giants. Jupiter, fifth planet from the Sun, contains more mass than all other planets combined. It's so large that 1,300 Earths could fit inside it. So massive that its gravity nearly prevented it from being a planet at all. A bit more mass, and Jupiter would have ignited fusion, becoming a second star in our system. But it didn't. It remains a planet. A gas giant composed mostly of hydrogen and helium, with perhaps a small rocky core buried under tens of thousands of kilometers of crushing atmosphere. And Jupiter is round, though not as round as Venus or Earth. Because Jupiter rotates incredibly fast, one complete rotation every 9 hours and 55 minutes. The centrifugal force creates a pronounced bulge at the equator. The equatorial diameter is 143,000 kilometers. The polar diameter is only 133,000 kilometers. That's a 10,000 kilometer difference, about 7% variation from a perfect sphere. Research shows this is the most oblate planet in our solar system. If you could look at Jupiter from above its north pole, it would appear noticeably flattened like a ball someone sat on. And yet, it's still spherical in the most important sense. Gravity still dominates. The shape still represents hydrostatic equilibrium, just adjusted for rapid rotation. Scientists studying Jupiter have found something beautiful in those swirling cloud bands. The great red spot storms, larger than Earth, that have raged for centuries, winds reaching 400 kilometers per hour, all that chaos, all that turbulence contained within a spherical envelope. It seems as though even violence given enough mass to work with arranges itself into roundness. Saturn, famous for its rings, shows even more extreme oblateness. It rotates every 10 hours and 33 minutes, even faster than Jupiter. And it's less dense, so much less dense, that if you could find an ocean large enough, Saturn would float. That combination of rapid rotation and low density creates a dramatic flattening. Saturn's equatorial diameter is 120,000 kilometers. Its polar diameter is only 108,000 kilometers. A 12,000 kilometer difference, about 10% variation. From certain angles, Saturn looks almost squashed like an egg viewed from the side. But consider those rings for a moment. They're made of countless particles, ice chunks, ranging from dust grain size to house-sized boulders, all orbiting Saturn in an impossibly thin disk. The rings stretch hundreds of thousands of kilometers across, but they're only 10 to 100 meters thick. Why so thin? Because gravity pulls them towards Saturn's equatorial plane, and any particle that drifts above or below gets tugged back. The rings are flat, for the same reason planets around gravity seeking equilibrium, minimizing energy, finding the most stable configuration. And what do those ring particles orbit? A sphere. Flattened by rotation? Yes, but undeniably spherical in its fundamental geometry. Some believe Saturn might be the most visually striking proof that gravity shapes everything it touches. The planet itself rounded by its own mass. The rings flattened by orbital mechanics. Dozens of moons, each one a smaller sphere, all dancing in gravitational choreography that's remained stable for billions of years. Uranus and Neptune, the ice giants, drift even farther out, where sunlight grows faint and temperatures plunge. Both are spherical. Both show equatorial bulges. From rotation, both maintain that essential roundness, despite being composed of materials we rarely think of as planetary water, ice methane, ice ammonia, ice layered around rocky cores. Uranus has a peculiarity. It rotates on its side, tilted 98 degrees from the plane of its orbit. Scientists suggest this might have resulted from a massive collision early in the solar system's history, an impact so violent it knocked the entire planet over. And yet, even after such trauma, Uranus remained round. Gravity reasserted itself, found equilibrium again. The scars of that ancient collision have long since healed, absorbed into the planet's structure. Neptune, discovered in 1846 through pure mathematics before anyone saw it through a telescope, completes our tour. It's the densest of the giant planets, with winds reaching 2,000 kilometers per hour, the fastest in the solar system. And a deep blue color from methane in its atmosphere. Round, like its siblings. Round, like everything, with sufficient mass. Research shows that all 8 planets, despite their differences, rocky or gaseous, hot or cold, fast rotating or slow, all achieved the same fundamental shape. Not because they're the same, but because gravity applies the same rules to everything. Mass plus time equals sphere. It's a formula simpler than any equation, more reliable than any law we've written in textbooks. Have you ever wondered why we don't see cubic planets or pyramidal moons? It's not chance. It's not probability. It's inevitability. Any object massive enough for its gravity to overcome the structural strength of rock will pull itself into a sphere. Anything smaller might remain irregular We'll explore those in just a moment, but anything large enough becomes round whether it wants to or not. Scientists suggest this might be why finding exoplanets around other stars has been so successful. We've discovered thousands of them now, orbiting distant suns, ranging from scorching hot Jupiters to frozen super-Earths. We've never seen most of them directly. They're too far away, too faint. But we know they're round. We know because they have enough mass to be planets, and planets are always round. It's one of the few certainties we have about worlds we'll likely never visit. The solar system, seen from a distance, is a portrait of gravity's artistic consistency. 8 spheres orbiting a larger sphere, following elliptical paths, determined by gravitational mathematics, worked out by Johannes Kepler 400 years ago. Each planet, a different size, a different composition, a different history, but all sharing that essential geometry, that roundness born from the same force that holds you against Earth. Right now, it seems as though the cosmos might be less diverse than it appears. Beneath surface differences, atmospheres and temperatures, rock and gas, the underlying structure remains constant. Spheres within spheres, curves within curves. Geometry born from gravity, from mass, from time. But the solar system holds other objects, 2 smaller ones, objects that haven't quite achieved planetary status, moons that orbit planets, asteroids that tumble through space, dwarf planets balanced on the edge of roundness. These in-between worlds, these threshold objects, can teach us exactly where the line between sphere and non-sphere lies, where gravity's influence becomes too weak to shape, where irregularity is allowed to persist. And those borderlands of roundness are waiting for us to explore them just ahead, in the quiet. Somewhere between planet and pebble, there's a line, a threshold where gravity becomes strong enough to pull an object into roundness, where mass overcomes the strength of rock and ice, where chaos surrenders to geometry. Above that line, spheres emerge inevitably. Below it, shapes remain wild, jagged, irregular, free. The question is, where exactly does that line fall? And what happens to the objects that live right on the edge, balanced between roundness and disorder, between becoming a sphere and remaining a fragment? Those borderland worlds, those threshold objects, might teach us more about gravity's patient architecture than any perfect planet ever could. If these wanderings through the cosmos bring you comfort, a moment of stillness in the night, you're welcome to mark your presence, a like to acknowledge the journey, a subscription to continue exploring together, a bell, so the next quiet story can find you. We're mapping the edges of roundness tonight, discovering where gravity's influence fades and where it holds strong. Now let's drift toward those edges. In the outer solar system, orbiting Saturn at a distance of about 186,000 kilometers, there's a moon that almost didn't make it, a moon that achieved roundness by the narrowest of margins, that pulled itself together, just barely, just enough. Its name is Mimas, and it measures 396 kilometers in diameter. Research shows that Mimas represents something close to the minimum size for an icy body to achieve hydrostatic equilibrium. Any smaller, and its gravity would be too weak to overcome the structural strength of ice. Any smaller, and it would remain potato-shaped, irregular, incomplete. But Mimas crossed that threshold, just barely. Look at photographs of this moon, and you'll see something haunting. The surface is almost perfectly spherical smooth in its overall curvature, but it's also heavily cratered, battered by billions of years of impacts. One crater dominates everything else. Herschel crater, named after the astronomer who discovered Mimas in 1789. Herschel measures 130 kilometers across 1/3 the diameter of Mimas itself. It's so large, so deep, that the impact which created it nearly shattered the entire moon. Scientists have found fractures on the opposite side of Mimas, directly across from Herschel cracks, in the ice caused by shock waves propagating through the moon's interior. The impact almost broke Mimas apart into debris and fragments that would never again be round. But gravity held, pulled the pieces together, maintained that hard-won equilibrium. Some believe Mimas might represent the absolute edge of roundness for icy bodies, the smallest object in the solar system that managed to achieve spherical shape through its own gravity alone. Scientists suggest this makes Mimas a kind of geological experiment, a natural test of where the boundary lies. Smaller icy moons in the Saturn system, Prometheus, Pandora, Epimetheus, all remain irregular potato-like because they don't have quite enough mass. Mimas does. Just enough. It's the difference between 396 kilometers and 350 kilometers, between barely sufficient gravity and insufficient gravity, between sphere and fragment. That margin is thinner than you might imagine. Now drift inward toward another threshold world, one that confused astronomers for decades, because it shouldn't be round, but is one that broke the rules scientists thought they understood. Ceres' largest object in the asteroid belt measures about 940 kilometers in diameter. For more than 2 centuries after its discovery in 1801, astronomers classified it as an asteroid. Just another chunk of rock tumbling between Mars and Jupiter, one among hundreds of thousands. But when NASA's Dawn spacecraft arrived at Ceres in 2015, it revealed something unexpected. Ceres isn't rocky like most asteroids. It's about 25% water ice by mass, with a rocky core surrounded by an ice mantle topped with a dusty crust. And it's round. Noticeably, measurably round. The Dawn mission found that Ceres has separated into layers based on density, with heavy elements sinking toward the center and lighter materials floating upward. This is something that only happens when an object has been massive enough for its interior to become warm, soft fluid. Research shows that Ceres likely had a subsurface ocean in its past, and might still have pockets of liquid water beneath its surface today. The spacecraft detected bright spots in Occator crater deposits of sodium carbonate that suggest briny water seeping up from below, evaporating, leaving mineral residue behind. A dwarf planet with an ocean. An asteroid belt object that achieved planetary processes, a world that crossed the threshold from fragment to sphere and kept going, developing geology, chemistry, perhaps even the basic ingredients for life. Scientists reclassified Ceres in 2006, the same year they reclassified Pluto. It's no longer considered an asteroid. It's a dwarf planet, round enough, massive enough to deserve planetary status, even if it hasn't cleared its orbit of other debris. It seems as though the universe doesn't care much about our categories. It only cares about mass and gravity and time. But here's what's remarkable. Ceres achieved roundness at 940 kilometers diameter. Mimas achieved it at 396 kilometers. Why the difference? The answer lies in what they're made of. Ice is weaker than rock. It deforms more easily under pressure. That means an icy body can achieve hydrostatic equilibrium at smaller sizes than a rocky body, because ice will flow and compress and round itself with less gravitational force. Rocky asteroids need to be larger, generally between 600 and 1,000 kilometers in diameter, before their gravity becomes strong enough to overcome rock's structural strength. Scientists have found several examples of large rocky asteroids that remain stubbornly irregular. Vesta, the second largest asteroid belt object at 525 kilometers diameter, is distinctly non-spherical. It has a massive mountain at its south pole. Rhea Silvia, rising about 22 kilometers above the surrounding terrain, proportionally much taller than anything on Earth. Vesta hasn't quite achieved roundness because rock is strong, and 525 kilometers isn't quite enough mass to overcome that strength. Pallas, third largest at 512 kilometers, shows even more irregularity. Photographs reveal an oblong shape, a world that looks more like a giant potato than a sphere. It has enough mass to have differentiated, to have separated into layers, but not quite enough to pull itself fully round. These objects live in the in-between zone, the threshold region, where gravity and material strength are nearly balanced, where the outcome depends on composition and thermal history and 100 other subtle factors. Research shows there's no single sharp line dividing round from non-round. Instead, there's a gradient, a transition zone, where some objects make it and others don't, depending on their specific circumstances. It's like watching evolution in slow-motion natural selection, operating on geology instead of biology, with gravity doing the selecting. Now drift outward again, past the asteroid belt, into the realm of Saturn's moons, where some of the strangest threshold objects in the solar system orbit in silent choreography. Enceladus, measuring 504 kilometers in diameter, is almost perfectly spherical. Larger than Mimas, it had an easier time achieving roundness. But what's remarkable about Enceladus isn't its shape. It's what's happening beneath that smooth, icy surface. In 2005, the Cassini spacecraft flew past Enceladus and detected something astonishing: plumes of water vapor erupting from cracks near the moon's south pole, shooting hundreds of kilometers into space. These weren't just icy geysers. They were evidence of a global ocean beneath the surface, an ocean in contact with a rocky core, an ocean that might harbor conditions suitable for life. Scientists suggest the tidal heating, the constant flexing caused by Saturn's gravity as Enceladus orbits in an elliptical path, keeps that ocean liquid despite surface temperatures of minus 200 degrees Celsius. The same gravitational force that pulled Enceladus into a sphere also maintains geological activity, keeps the interior warm, prevents the ocean from freezing. It seems as though roundness and activity are connected. Once an object achieves hydrostatic equilibrium, once it becomes large enough for gravity to shape it, other processes often follow. Differentiation, internal heat, geological activity, sometimes even oceans, but not always. Compare Enceladus to Mimas, its neighbor in the Saturn system. They're similar in size. Enceladus is only about 100 kilometers larger. Both are round. Both orbit Saturn. Both experience tidal forces. Yet, Enceladus is active, erupting, warm. Mimas is dead, frozen, ancient. The difference might come down to orbital resonance, the way Enceladus's orbit is locked in a 2-to-1 ratio with another moon Dione, creating stronger tidal heating. Or it might be composition, internal structure, chance. Scientists don't fully understand why some threshold moons are active and others aren't. The variables are many. The systems are complex, but the pattern is clear. Once you cross into roundness, new possibilities open up. New processes become available. Roundness isn't just about shape, it's about transformation. Consider the outer solar system's captured moons, irregular satellites that probably didn't form where they orbit now, but were captured by planetary gravity from elsewhere. Jupiter has dozens of them. Saturn has many. Neptune has one particularly famous example, Triton. Triton measures 2,700 kilometers in diameter, making it the 7th largest moon in the solar system. It's round, clearly round, easily massive enough for hydrostatic equilibrium. But it orbits Neptune backward retrograde, opposite to the planet's rotation. Research shows this backward orbit is strong evidence that Triton didn't form around Neptune. Instead, it likely originated in the Kuiper belt beyond Neptune's orbit and was captured billions of years ago in a gravitational encounter so violent it probably destroyed other moons that were orbiting Neptune at the time. And yet, despite that violent history, Triton is round. It was probably already round before capture, already large enough for its own gravity to shape it. Scientists studying Triton have found nitrogen geysers on its surface, evidence of a thin atmosphere, and a temperature of minus 235 degrees Celsius, making it one of the coldest surfaces in the solar system. But it's geologically active, young. Some regions show terrain that appears to be less than 100 million years old. Gravity didn't just shape Triton's body. It captured it, relocated it, subjected it to immense tidal forces during capture that heated the interior and erased whatever ancient surface features it once had. It seems as though even at the edge of the solar system, even in the frozen darkness beyond Neptune gravity, continues its patient work of shaping, smoothing, rounding. But there are limits. There are objects that will never be round, no matter how long you wait, because they simply don't have enough mass. The asteroid Ida, visited by the Galileo spacecraft in 1993, measures about 58 kilometers long and looks like an elongated potato with craters. Its gravity is so weak that if you stood on its surface, you could probably jump off entirely, escape into space, just by pushing hard against the ground. Comet 67P/Churyumov-Gerasimenko, visited by the Rosetta spacecraft in 2014, has an even stranger shape. 2 lobes, connected by a narrow neck, like a rubber duck floating through space. Scientists suggest it might be 2 separate objects that collided gently and stuck together too small for gravity to merge them into a single sphere. These objects show us what happens below the threshold. No differentiation, no internal heat, no geological processes, just cold rock or ice tumbling through space, preserving impact craters billions of years old. because there's no mechanism to erase them. They're geologically dead, not because they're old, but because they were never alive, never large enough for gravity to generate heat motion change. Research in planetary science has revealed something beautiful about this threshold. It's not just about size, it's about potential. Objects above the threshold can evolve, change, develop complexity. Objects below it are frozen in their initial state, unchanging witnesses to the solar system's formation. Scientists studying asteroids have found that some of them are actually rubble piles, collections of fragments held together loosely by gravity, with voids and gaps in their interiors. They're not solid objects at all, just debris that happens to be traveling together. These rubble piles could never be round, because they're not even unified objects. They're communities of fragments, and communities don't have shape beyond the collective outline of their members. It seems as though there are layers to this threshold. First, you need enough mass for gravity to hold you together as a single object instead of a rubble pile. Then, you need enough mass for that gravity to deform the material into roundness. Then, if you have even more mass, you get differentiation, heat, activity, oceans. Each threshold opens new possibilities. Each step in mass creates new complexity. Have you ever noticed how satisfying it feels to organize things, to sort items by size or color or category? There's something deeply calming about seeing order emerge from chaos, about drawing lines and establishing boundaries. The solar system does this naturally through gravity. It sorts objects into categories: planets, dwarf, planets, moons, asteroids, comets based on nothing but mass and orbital characteristics. And within those categories, it sorts further round or irregular active, or dead differentiated, or primitive, all without anyone organizing it, all through the patient, mindless operation of physical law. We've explored the threshold where roundness begins, where gravity becomes strong enough to shape. We've seen moons like Mimas hanging right at the edge, barely round. We've seen Ceres crossing from asteroid to dwarf planet. We've seen Enceladus achieving not just roundness, but activity, life-supporting chemistry. But these are all cold worlds, frozen spheres heated only intermittently by tidal forces or radioactive decay. They show us what gravity can do with ice and rock and limited energy. To see what gravity builds when it has truly vast amounts of mass and energy to work with, we need to look at stars themselves, at fusion-powered spheres that burn for billions of years, where gravity and pressure battle in perfect balance, creating light, creating elements, creating the very atoms that make up everything we've discussed so far. And those stellar spheres, those furnaces in the darkness, are waiting for us just ahead. Deep in the heart of every star, there's a war being fought. Not with weapons or armies, but with forces so fundamental they define what matter can become. Gravity pulling inward, trying to crush everything into infinite density. Pressure pushing outward, trying to tear the star apart. And between those opposing forces for billions of years, a perfect balance holds. That balance creates light, creates heat, creates every element heavier than hydrogen that exists in the universe, including the atoms that make up your body right now. And it creates, inevitably, a sphere. Because when two forces push against each other equally from all directions, when compression meets resistance at every point, there's only one shape that satisfies both demands: roundness. Again, always. If these journeys through cosmic architecture, bring you a sense of peace of connection to something larger, you might want to gently mark your presence. A like says you're here with me. A subscription means we'll continue exploring together. The bell lets the next quiet story find you when you need it most. We're witnessing how gravity births stars tonight, how it shapes furnaces that burn longer than civilizations last. Let's begin where all stars begin, in darkness and cold. Molecular clouds drift through the galaxy, vast regions of gas and dust, so diffuse they're nearly invisible. So cold, they hover just a few degrees above absolute zero. Some of these clouds stretch for hundreds of light years, containing enough material to birth thousands of stars. And yet, despite their size, they're barely there. The density inside a molecular cloud is about 1,000 hydrogen molecules per cubic centimeter, far more tenuous than the best vacuum we can create in laboratories on Earth. If you could stand inside one, you wouldn't notice. It would feel like empty space. But gravity notices. Gravity always notices mass, no matter how thinly spread. Research shows that molecular clouds exist in a delicate balance. The internal pressure from gas pushing outward exactly equals the gravitational pull trying to compress the cloud inward. As long as that balance holds, the cloud just drifts unchanging for millions of years. But sometimes, something disturbs the balance. A nearby supernova sends shock waves rippling through the cloud. A collision with another cloud creates regions of higher density, or perhaps the cloud simply grows large enough that gravity, patient and persistent, begins to win. When that happens, a small region within the cloud starts to collapse. As it collapses, it heats up. Basic physics: when you compress a gas, its temperature rises. The same principle that makes a bicycle pump warm when you inflate a tire. Except instead of a few degrees, this collapse creates temperatures of thousands, then millions of degrees. Scientists call this collapsing region a protostar. It's not quite a star yet. It's not hot enough for fusion. But it's getting there, growing denser and hotter and more massive as material from the surrounding cloud falls inward, pulled by its strengthening gravity. And here's what matters. For our story, from the very beginning, even before fusion ignites, the protostar is round. Because gravity pulls equally from all directions. Because the collapsing gas is rotating, flattening into a disk around the equator, but maintaining spherical symmetry overall. Because pressure pushes back equally, creating hydrostatic equilibrium. Some believe this early roundness might be imprinted into stellar formation, a template that persists even as the star evolves, even as it swells into a red giant, or collapses into a white dwarf billions of years later. The transition from protostar to star happens when the core reaches about 10 million degrees Celsius. At that temperature, hydrogen nuclei moving so fast, colliding with such force, can overcome the electromagnetic repulsion between their positive charges and fuse together. 4 hydrogen nuclei combine to create 1 helium nucleus, releasing energy in the process. That energy radiates outward as light as heat as the radiation pressure that stops the gravitational collapse. The star turns on. Our sun ignited about 4.6 billion years ago, joining the roughly 100 billion other stars in the Milky Way galaxy. It started with a mass about 70% of what it has now, gradually accumulating more material from its surrounding disk over the first few million years. Research shows that young stars are turbulent, unstable, prone to dramatic flares and eruptions as they adjust to the new balance between gravity and fusion. But even during that chaotic youth, the sun maintained its spherical shape. Because hydrostatic equilibrium doesn't require stillness. It only requires balance. As long as the inward pull of gravity equals the outward push of pressure at every point, the star remains round, regardless of what's happening inside. Scientists studying the sun today have measured its shape with extraordinary precision. The equatorial diameter is 1,392,684 kilometers. The polar diameter is 1,392,670 kilometers. That's a difference of only 14 kilometers out of nearly 1.4 million kilometers total. Less than 0.001% variation from a perfect sphere. For comparison, if you shrunk the sun down to the size of a basketball, that 14-kilometer difference would be smaller than the thickness of a human hair. It seems as though the sun, burning with such violence at its core, creating temperatures of 15 million degrees, generating enough energy to power photosynthesis on Earth, 150 million kilometers away, somehow maintains near-perfect roundness through all that chaos. The secret lies in the battle itself. Gravity doesn't just pull matter inward randomly. It pulls toward the center of mass, which for a rotating sphere is the exact geometric center. Any region that bulges too far outward feels stronger gravity pulling it back. Any region that collapses too far inward generates higher pressure that pushes it back out. The system self-corrects constantly, billions of times per second, across every cubic centimeter of the sun's interior. Research in helioseismology, the study of waves propagating through the sun, has revealed that the entire star rings like a bell, vibrating with thousands of different oscillation modes. Some regions move inward, while others move outward, creating waves that travel through the solar interior at speeds of thousands of kilometers per hour. And yet, the average shape, the equilibrium configuration around which all these oscillations occur, remains spherical. Scientists suggest this might be one of the most remarkable things about stars. They're not static objects. They're dynamic, churning, constantly adjusting. But their overall geometry is stable, maintained by forces so precisely balanced that they can persist for billions of years. Our sun is about halfway through its life. In another 5 billion years, when the hydrogen in its core runs out, fusion will stop. Gravity will begin to win. The core will collapse, heating up until it's hot enough to fuse helium into carbon. And when that happens, the outer layers of the sun will expand dramatically, swelling into a red giant hundreds of times larger than the sun is now. Large enough to swallow Mercury, Venus, possibly Earth. But even then, even swollen to such vast size, the sun will remain spherical. The same balance will hold gravity, inward pressure outward, just at a much larger radius. Some believe that red giants might be the most visually striking proof that stars maintain roundness through every phase of their evolution. Betelgeuse, the red supergiant in the constellation. Orion has a diameter about 700 times larger than our sun. If you placed it where our sun is, its surface would extend beyond Mars's orbit. And yet, observations from interferometric telescopes that can resolve Betelgeuse's actual disk show it's still round. Noticeably, measurably round, despite being so tenuous that its outer layers are barely denser than the vacuum of space. Research shows that Betelgeuse will eventually explode as a supernova, probably within the next 100,000 years tomorrow on cosmic timescales. When it does, it will briefly outshine the entire galaxy, visible in daylight from Earth, creating heavy elements that will seed the next generation of stars and planets. But until that moment, gravity and pressure continue their ancient balance, maintaining sphericity, even in a star so near the end of its life. Now consider stars at the opposite extreme, stars, far more massive than our sun stars, that burn so hot and bright they exhaust their fuel in just a few million years instead of billions. The most massive stars known can reach up to 300 times the sun's mass. At that scale, the internal pressure from fusion is so intense it nearly tears the star apart from within. These stars lose mass, constantly shedding their outer layers in powerful stellar winds, blasting material into space at thousands of kilometers per second. Scientists studying these massive stars have found they're less perfectly spherical than smaller stars like our Sun. Rapid rotation causes significant equatorial bulging. Powerful magnetic fields create active regions and star spots. Mass loss can create asymmetric outflows, and yet the fundamental geometry remains spherical. The deviations are small percentages, irregularities superimposed on an underlying sphere. It seems as though no matter how massive a star becomes, no matter how violent its interior processes, gravity's patient insistence on symmetry prevails. But there are failed stars. 2. Objects that tried to become stars, but didn't quite make it. Objects that show us where the lower boundary of stellar formation lies. Brown dwarfs form the same way stars do, from collapsing molecular clouds, but they never accumulate enough mass for hydrogen fusion to ignite. The threshold sits at about 13 Jupiter masses, or roughly 0.013 solar masses. Below that threshold, the core never gets hot enough. Gravity compresses the interior. Temperatures rise, pressure builds, but it's not quite enough. The object settles into a lukewarm sphere, glowing faintly in infrared from residual heat, slowly cooling over billions of years. Research shows that brown dwarfs occupy a strange middle ground between planets and stars. They're more massive than any planet, but less massive than any true star. They have weather atmospheric circulation, possibly even lightning. Some have moons orbiting them, and they're round, obviously round, because they have more than enough mass for hydrostatic equilibrium, even if they don't have enough for fusion. Scientists suggest there might be billions of brown dwarfs drifting through the galaxy, too dim to see easily, too small to be stars, too large to be planets. Failed attempts at stellar birth, frozen at the threshold, forever almost stars. It's strangely melancholy, isn't it? Objects massive enough to pull themselves into spheres, but not massive enough to light up, to burn, to create. But consider what happens when stars do succeed, when they burn through all their fuel and face their final transformations. Stars like our Sun, average mass unremarkable, will eventually shed their outer layers in a planetary nebula, leaving behind a white dwarf at the center. A white dwarf is an extraordinary object, roughly the mass of the Sun, compressed into a sphere about the size of Earth. The density is staggering. A teaspoon of white dwarf material would weigh about 5 tons on Earth. Electrons are packed so tightly they enter a quantum state called electron degeneracy, where they can't be compressed any further because quantum mechanics forbids it. And white dwarfs are round, perfectly unchangingly round. No fusion occurs inside them. There's no more fuel to burn. They just sit there cooling slowly, glowing from residual heat maintained in spherical shape by the balance between gravity and electron degeneracy pressure. Research shows that white dwarfs cool so slowly it takes trillions of years for them to fade completely. The universe is only about 13.8 billion years old, so even the oldest white dwarfs are still glowing faintly, still visible. And every one of them is a sphere, because even in death, even as embers cooling in the cosmic darkness, the fundamental balance between inward pull and outward resistance continues. Scientists have calculated that there's a maximum mass for white dwarfs discovered by Subrahmanyan Chandrasekhar in 1930. The Chandrasekhar limit sits at about 1.4 solar masses. Above that mass electron degeneracy pressure isn't strong enough to resist gravity. When a white dwarf exceeds that limit, usually by pulling matter from a companion star, it collapses catastrophically. Electrons and protons are forced together, forming neutrons, and the star transforms into something even stranger. A neutron star. Neutron stars are perhaps the most extreme spherical objects in the universe that aren't black holes. They pack about 1.4 solar masses into a sphere only about 20 kilometers in diameter. That's roughly the size of a large city. The density is beyond comprehension. A teaspoon of neutron star material would weigh about 1 billion tons. The surface gravity is so strong that if you could somehow stand on a neutron star, you'd weigh about 100 billion times more than you do on Earth. And yet, despite these extremes, despite gravity so intense, it warps space-time measurably. Neutron stars are round. Research from pulsar observations rotating neutron stars that emit beams of radiation like cosmic lighthouses shows that these objects maintain spherical symmetry even while spinning hundreds of times per second. Some pulsars rotate so fast their equators are moving at significant fractions of the speed of light, creating enormous centrifugal forces. But the gravity is stronger, always stronger. The shape bulges slightly at the equator, yes, but remains fundamentally spherical. Scientists studying neutron stars have found that there's a maximum mass for them too, called the Tolman-Oppenheimer-Volkoff limit, somewhere between 2 and 3 solar masses. The exact value depends on the properties of matter at nuclear densities which we don't fully understand. Above that limit, not even neutron degeneracy pressure can resist gravity. The star collapses further, compressing beyond the point where any known force can stop it crossing the threshold, where escape velocity exceeds the speed of light. It becomes a black hole. And black holes, those final endpoints of stellar evolution, represent gravity's ultimate expression of sphericity. Not in their matter, we don't know what happens to matter inside a black hole, but in their geometry, in the shape of space-time itself around them. The event horizon, the boundary beyond which nothing can escape, is perfectly spherical for a non-rotating black hole. It has to be. Any asymmetry would radiate away as gravitational waves until perfect symmetry was restored. It seems as though even when matter itself is crushed out of existence, when we reach the very limits of what physics can describe, The sphere remains, gravity's preferred shape, the universe's final answer to the question of form. From molecular clouds to protostars, from main sequence stars to red giants, from white dwarfs to neutron stars, we've traced stellar evolution across billions of years and watched roundness persist through every transformation. We've seen how the battle between gravity and pressure creates not just shape, but light heat, the very elements that make planets and life possible. But stars create more than elements. They create the most extreme geometric objects in existence. Objects where gravity becomes so strong, it rewrites the rules of space and time itself. Where spheres exist, not as surfaces, but as horizons, as boundaries between what can be known and what is forever hidden. And those ultimate spheres, those final sculptures of gravity's absolute dominance, are waiting for us in the deepest darkness. Imagine a place where gravity is so strong that nothing can escape. Not rocks or gas, not planets or light, not even information itself. A region of space-time so warped, so compressed, that the normal rules of physics break down and something stranger takes over. A boundary in space beyond which everything that enters is lost forever, falling toward a center that might not even exist in any meaningful sense. That boundary has a shape, and perhaps you've already guessed what it is. A sphere. Perfect, inevitable, inescapable. Black holes represent gravity's final victory, the ultimate expression of what happens when mass concentrates so intensely that nothing, not even the fabric of space-time itself, can resist its pull. If you've stayed with me through this long, gentle drift across the cosmos, if these quiet explorations bring you peace in the darkness, you might want to mark this moment. A like to acknowledge we've traveled far together. A subscription to continue these journeys through deep space and deeper time. A bell so the next story can find you when silence returns. We're approaching the edge of what can be known tonight, the boundary where physics itself transforms. Let's begin at that boundary at the event horizon. The term was coined in 1956 by Wolfgang Rindler, though the concept is older, dating back to 1783, when Jean Michel first imagined dark stars so massive that light couldn't escape them. But it was Carl Schwarzschild in 1916, just months after Einstein published General Relativity, who first calculated the exact geometry. Schwarzschild was serving in the German army during World War I, stationed on the Russian front, when he solved Einstein's field equations for the case of a spherically symmetric, non-rotating mass. Despite the chaos of war, despite being far from any university or laboratory, he found an exact solution. What he discovered was both elegant and disturbing for any given mass. There exists a radius at which space-time curvature becomes so extreme that the escape velocity equals the speed of light. Inside that radius, nothing escapes. Outside, escape is still possible, though difficult. That radius is now called the Schwarzschild radius, and the spherical surface it defines is the event horizon. Research shows the formula is surprisingly simple. The Schwarzschild radius equals 2 times the gravitational constant times the mass divided by the speed of light squared. For the sun's mass, that radius is about 3 kilometers. For Earth's mass, it's about 9 millimeters. Of course, neither the sun nor Earth is actually a black hole, because their matter extends far beyond their Schwarzschild radii. But if you could compress the sun down to a sphere 6 kilometers across, it would become a black hole. If you could compress Earth to the size of a marble, same result. The event horizon would form automatically, inevitably, as a perfect sphere surrounding the compressed mass. Scientists suggest that this sphericity isn't optional. It's required by the mathematics of general relativity. Any deviation from perfect spherical symmetry would create asymmetric gravitational radiation ripples in spacetime, carrying away energy and angular momentum until the asymmetry was erased. Some believe this might be the most profound aspect of black holes. They have no memory of the shape of whatever formed them. A black hole created from a perfectly spherical star is indistinguishable from one created from an irregular, lumpy star. All the details are lost. Only 3 properties remain: mass, electric charge, and angular momentum. Everything else, composition, texture, history, is erased, forgotten, reduced to pure geometry. This is sometimes called the no-hair theorem. In physics, a playful term suggesting that black holes are bald featureless, described completely by just those 3 numbers. But here's where it becomes more complex, more interesting. The Schwarzschild solution describes a non-rotating black hole, and such objects probably don't exist in nature. Every star rotates. When a star collapses into a black hole, it conserves angular momentum, which means it must rotate faster as it shrinks like that ice skater pulling in their arms. The result is a rotating black hole, described by a different solution to Einstein's equations found by Roy Kerr in 1963. Research shows that rotating black holes, Kerr black holes, have event horizons that are still spherical, but with a crucial difference. They're oblate spheres, flattened at the poles and bulging at the equator, just like rotating planets, but far more extreme. And they have an additional feature, the ergosphere, a region outside the event horizon, where space-time itself is dragged around the black hole's rotation. Inside the ergosphere, you can't stand still even if you wanted to. Space itself is moving, carrying you along whether you like it or not. But even with rotation, even with this additional complexity, the underlying geometry remains spherical. The event horizon is a surface of constant distance from the black hole's center, a sphere deformed by rotation, but still fundamentally round. Scientists studying black holes have found that there are size limits thresholds similar to what we've seen with planets and stars, but at both extremes of the mass spectrum. At the small end, stellar mass black holes form from the collapse of massive stars, typically between 3 and 100 solar masses. Their event horizons range from about 9 kilometers to 300 kilometers in radius, small enough to fit inside a large city, yet containing the mass of dozens of suns. At the large end, supermassive black holes sit at the centers of most galaxies, including our own Milky Way. These monsters contain millions to billions of solar masses with event horizons stretching across tens of millions of kilometers, roughly the size of planetary orbits. The supermassive black hole at the center of our galaxy, Sagittarius A, contains about 4 million solar masses. Its event horizon has a radius of about 12 million kilometers, which sounds enormous until you realize that's still only about 0.08 astronomical units, less than 1/10 the distance from Earth to the Sun. Research from the Event Horizon Telescope collaboration, which produced the first direct image of a black hole's shadow in April 2019 targeted an even larger supermassive black hole, M87, in the center of the galaxy. Messier, 87, about 55 million light-years from Earth. M87-9 contains about 6.5 billion solar masses. Its event horizon spans about 20 billion kilometers, roughly 3 times the size of Pluto's orbit around our Sun. And when the Event Horizon Telescope team released their image, what did they show? A circular shadow. A ring of light bent around the event horizon by extreme gravitational lensing. And at the center, darkness in the shape of a near-perfect circle. Some believe this might be the most direct visual confirmation of sphericity we've ever obtained. Not just inference from mathematics or indirect measurements, but an actual image showing the circular outline of an event horizon captured by coordinating radio telescopes across the entire Earth to create an instrument the size of the planet. Scientists studying that image found that M87T's shadow matched the predictions of general relativity to within 10%. The black hole is rotating rapidly, which creates asymmetry in the surrounding accretion disk, matter spiraling inward, heating up, emitting brilliant radiation. But the event horizon itself remains round within measurement uncertainty. It seems as though, even at the most extreme scales, even where space-time is so warped that clocks run noticeably slower and light bends into closed loops, spherical symmetry persists. But what happens if you could somehow approach a black hole? What would you experience as you fell toward that spherical boundary? First, you'd notice tidal forces. Remember how the moon raises tides on Earth by pulling more strongly on the near side than the far side. The same thing happens near a black hole, but far more intensely. For a stellar mass black hole, the kind formed from a collapsed star, the tidal forces near the event horizon are enormous. If you fell feet first, gravity would pull more strongly on your feet than your head. You'd be stretched vertically and compressed horizontally, elongated like taffy, a process physicists call spaghettification. Research shows that for a black hole of 3 solar masses, the tidal forces would tear a human body apart long before reaching the event horizon, probably at a distance of about 400 kilometers from the center. But for a supermassive black hole like M87 Tau, something remarkable happens. Because the event horizon is so much larger, the gravitational gradient, the rate at which gravity changes with distance, is much gentler. You could cross the event horizon without feeling anything unusual, at least initially. Scientists suggest that for the largest supermassive black holes containing billions of solar masses, you might survive for several hours after crossing the event horizon, falling deeper into the black hole before tidal forces became fatal. Of course, you'd never be able to report what you saw because nothing can escape from inside the event horizon. Not light, not radio waves, not any form of information. From the perspective of someone watching you fall in from a safe distance, something stranger happens. As you approach the event horizon, you appear to slow down. Your clock runs slower relative to theirs due to gravitational time dilation. You get redder as the light you emit loses energy climbing out of the gravitational well. And just as you reach the event horizon, you appear to freeze, never quite crossing, becoming dimmer and redder until you fade from view entirely. Some believe this might be the strangest aspect of black holes, the disconnect between what infalling observers experience and what distant observers see. You cross the horizon and continue falling. They see you freeze at the boundary, asymptotically approaching, but never reaching. Both perspectives are correct, just measured in different reference frames. Research in gravitational physics has revealed that event horizons aren't physical surfaces. There's nothing there. No material. No barrier. Just a mathematical boundary where the causal structure of space-time changes, where future-directed paths all point inward toward the singularity. The singularity. That's what lies at the center, according to general relativity. A point of infinite density and infinite curvature, where the equations break down and physics as we understand it stops making sense. But scientists are fairly certain that real singularities don't exist. Most believe that quantum effects, which general relativity doesn't account for, must become important at extremely small scales and prevent true infinities from forming. What actually happens at the center of a black hole? Nobody knows. We'd need a theory of quantum gravity to describe it properly, and despite decades of effort, we don't have one yet. But here's what we do know. The event horizon itself, that spherical boundary, is real, measurable, observable, at least indirectly, through its effects on surrounding matter and light. Scientists studying black holes have found another remarkable property. They emit radiation. In 1974, Stephen Hawking showed that quantum effects near the event horizon should cause black holes to radiate energy, slowly, gradually, losing mass over time. This Hawking radiation is incredibly faint, far too weak to detect from any known black hole. But it suggests that black holes aren't entirely black. They glow barely in the quantum realm. And as they radiate, they shrink. The event horizon gets smaller, maintaining its spherical shape, but decreasing in radius as the mass decreases. Research shows that for a stellar mass black hole, the evaporation time is about 10 to the 67 years, an unimaginably long time, far longer than the current age of the universe. But for microscopic black holes, if they exist, evaporation would be much faster, potentially observable. Some believe this creates a profound tension in physics. If black holes evaporate completely, what happens to the information that fell into them? Is it destroyed, violating quantum mechanics? Or does it somehow escape, violating general relativity? This is the black hole. Information paradox still unresolved after 50 years of debate. But through all these questions, through all the uncertainty about what happens inside or at the quantum level, one thing remains clear. The macroscopic geometry is spherical. The event horizon is round. Consider what this means. Black holes are arguably the most extreme objects in the universe, the densest concentrations of mass, the strongest gravitational fields, the most warped space-time. They represent the absolute limit of what gravity can create, the end point of stellar evolution for the most massive stars. And they're spheres, not cubes or pyramids or some alien geometry we can't imagine. Just spheres the same shape as soap bubbles and planets and stars? It seems as though there's a deep unity to the cosmos, a consistency that extends from the smallest moons to the largest black holes. Wherever gravity dominates, wherever mass concentrates, spheres emerge. Not as design, but as consequence. Not as intention, but as inevitability. Scientists suggest this reflects something fundamental about the nature of space itself. Space is isotropic. It looks the same in all directions. It has no preferred orientation, no built-in asymmetry. So, When mass warps space, it warps it equally in all directions, creating spherical symmetry automatically. It's not that the universe prefers spheres. It's that space itself has no reason to prefer anything else. Have you ever wondered why the shape of gravity's influence feels so natural, so right? Why spheres appear in nature everywhere, from drops of water to distant galaxies? Perhaps it's because we evolved in a universe where gravity shapes everything large enough to notice where roundness is written into the geometry of space and time, where the pull toward centers creates curves wherever we look. We've traced gravity's architecture from the gentlest moons, barely holding themselves together, through planets and stars, burning bright to black holes, where space-time itself becomes a trap. At every scale and every context, the pattern holds. Mass plus gravity plus time equals sphere. But this long journey through cosmic geometry has been more than a catalog of round objects. It's been a meditation on inevitability, on how simple rules create complex beauty, on how the universe organizes itself without instruction or intention. And now, as we drift toward the end of this quiet exploration, it's time to gather these threads together, to reflect on what spheres tell us about the cosmos and our place within it, to find the gentle truths hidden in geometry and gravity and the patient work of time. That final reflection awaits us just ahead in the closing stillness. We've traveled far tonight, haven't we? From a single drop of water hanging in zero gravity to black holes swallowing light at the edge of forever. From Newton's garden to Einstein's curved space-time. From the smallest moons clinging to roundness by the thinnest of margins to stars burning for billions of years in perfect spherical balance. And through it all, one shape appeared again and again, like a melody, repeated in different keys, like a truth told in different languages. The sphere, not by coincidence, not by design, but by something deeper, quieter, more patient than either. By gravity working across billions of years, pulling matter toward itself with the gentlest insistence imaginable until chaos becomes order and disorder becomes geometry. Tonight, as we drift toward the end of this journey, let's gather what we've learned. Let's see what spheres can teach us, not just about the cosmos, but about the nature of existence itself. If these long wanderings through space and time have brought you comfort, given you something to wonder about as you drift toward sleep, you might want to leave a small marker of your passage. A like to say, you were here. A subscription to walk this path again. A bell to let the next gentle story find you in the darkness. We've explored the architecture of gravity together, you and I, and there are always more wonders waiting in the quiet. Now let's reflect. The story of spheres is really the story of equilibrium of forces finding balance. Every sphere in the universe represents a moment when inward pull and outward resistance reached an agreement, when compression and expansion negotiated a truce. For planets, the balance involves gravity pulling inward and the structural strength of rock pushing outward. For stars, it's gravity versus fusion pressure. For black holes, it's gravity versus the very geometry of space-time itself. But in every case, the result is the same. A shape where every point on the surface is equidistant from the center. A form with no edges, no corners, no preferred direction. A geometry that looks the same from every angle. Some believe this might reveal something profound about the universe's fundamental nature. Space itself has no built-in asymmetry. No up or down, no left or right that's universal. The laws of physics are the same in all directions, a property scientists call isotropy. So, when matter gathers under its own gravity, it shapes space isotropically, equally, fairly, and equal shaping from all directions can only create one form, a sphere. Research in cosmology suggests that even the universe itself might be spherical, at least the part we can observe. The cosmic microwave background, the afterglow of the Big Bang, is distributed almost perfectly evenly across the sky, with tiny fluctuations of only about 1 part in 100,000. That uniformity suggests the observable universe expanded symmetrically from a single point, creating a sphere of space centered on that origin. We can't see beyond that sphere because light from farther regions hasn't had time to reach us yet. But the shape of the cosmos, we can observe round. Spheres, within spheres, within spheres, all the way up. Scientists studying the history of astronomy have found that humans took a long time to accept this roundness, to understand what it meant. The ancient Greeks knew Earth was spherical. Pythagoras suggested it in the 6th century BCE, and Aristotle proved it in the 4th century BCE by observing Earth's curved shadow on the moon during lunar eclipses. But it took until Galileo in 1610 to prove that other planets were spherical too. His telescope revealed that Venus went through phases like the moon, which only made sense if Venus was a sphere illuminated by the sun from different angles. And it took until the 1960s, with the first photographs from space for most of humanity, to see Earth's roundness with their own eyes, to viscerally understand that we live on a sphere floating in darkness. Some believe this might be why flat Earth theories persist even now. Because our immediate experience is of flatness, the ground beneath our feet, the horizon extending to what seems like an edge. Roundness is too large to perceive directly. It requires abstraction, measurement trust, in what mathematics and observation reveal, rather than what immediate sensation suggests. But the evidence is overwhelming. Ships disappear hull first over the horizon. Different stars are visible from different latitudes. Time zones exist because Earth rotates. Satellites orbit in paths that only make sense if Earth is round. And more than that, roundness makes sense. It's the inevitable result of gravity acting on mass over time. It's what happens when you let nature organize itself without interference. It seems as though accepting Earth's sphericity means accepting a larger truth, that reality doesn't always match immediate perception, that the universe operates according to principles that reveal themselves through careful observation rather than casual glance. Consider what it means that you're resting on a sphere right now. Not metaphorically, literally. The atoms of your body are being pulled toward the center of a sphere, 12,700 kilometers in diameter, held against its curved surface by gravity that has been pulling for 4.5 billion years. Every breath you take happens on the skin of that sphere. Every step you walk traces a curve around its surface. Every horizon you see is the visible edge of that curvature, the point where the sphere's surface curves away from your line of sight. You've never stood on flat ground. That's an illusion created by the immense size of the sphere compared to your small body. But it's a sphere nonetheless, and you've been following its curves your entire life. Research in human perception shows that our brains are extraordinarily good at creating simplified models of reality, at taking complex, three-dimensional geometry and reducing it to manageable mental maps. That's why flat Earth intuitions persist. Our brains evolved to navigate small regions, not to comprehend planetary scale. But understanding overcomes intuition. Knowledge reveals what sensation conceals. Scientists suggest that this might be one of the most important lessons spheres teach us, that the universe is stranger and more wonderful than everyday experience suggests. But that strangeness follows, rules, obeys patterns, makes sense once you learn its language. And gravity speaks in spheres. Have you noticed how satisfying roundness feels, not just visually, but conceptually? There's something complete about circles and spheres, something finished. They have no beginning or end. They enclose space perfectly. They're efficient and elegant and balanced. Maybe we find spheres beautiful because they represent resolution. They're what matter becomes when all the violence is over, when the collisions have finished, when the chaos has settled. They're the shape of peace after war, of stillness after motion, of equilibrium after struggle. Every planet is a memoir of violence smoothed by time. Every star is a battle frozen in geometry. Every sphere tells a story of forces that once fought and now rest in balance. Some believe this might be why contemplating spheres is calming. They remind us that chaos is temporary, that disorder given enough time becomes order, that even the most violent beginnings can lead to stable, beautiful endings. 4.5 billion years ago, Earth was a hellscape of molten rock bombarded constantly by asteroids spinning wildly, nothing like the gentle blue sphere we know today. But gravity waited, pulled, smoothed, and eventually inevitable as sunrise roundness emerged. The same thing happened throughout the solar system, throughout the galaxy, throughout the universe. Everywhere mass-gathered spheres formed, not quickly. Geological time is patient beyond human comprehension, but reliably, inevitably, like water finding level. Research in planetary science has revealed that this process is still happening. Moons are still settling into roundness. Dwarf planets in the outer solar system are still differentiating, still organizing their interiors. The cosmos is a work in progress, and spheres are its preferred medium. Scientists studying exoplanets, planets orbiting other stars, have discovered thousands of worlds in recent decades. We've never seen most of them directly. They're too far away, too faint. We detect them by the tiny wobbles they create in their host star's motion, or by the slight dimming when they pass in front of those stars. But we know they're round. We know because they're massive enough to be planets, and planets are always round. It's one of the few certainties we have about worlds we'll likely never visit. Somewhere out there, orbiting a star, we can barely see, there might be a planet not too different from Earth. Rocky, watery, orbiting in the habitable zone where temperatures allow liquid water to exist. And it's round, absolutely certainly round, because gravity shapes all worlds the same way, regardless of where they form or what they're made of. It seems as though spheres might be universal, a constant across all of space and time, wherever matter exists and gravity operates. Consider what this means for the search for life beyond Earth. We don't know if life is common in the universe. We don't know what forms it might take, what chemistry it might use, what environments it might thrive in. But we know the worlds it inhabits will be round if they're large enough. We know those worlds will orbit stars that are also round. We know the geometry of gravity is the same everywhere. Some believe this might be one of the most profound unities in existence, that despite the unimaginable diversity of conditions across the cosmos, despite temperatures ranging from near absolute zero to billions of degrees, despite pressures from perfect vacuum to the crushing force inside neutron stars, the fundamental architecture remains constant. Mass gathers, gravity pulls, spheres emerge. It's a pattern so reliable it feels almost like a law, though it's really just a consequence of deeper laws. The law of gravitation, the principle of least action, the symmetry of space itself. Scientists suggest that if we ever encounter alien artifacts, objects built by intelligence from other worlds, one way to recognize them would be deviation from sphericity. Natural objects are round or irregular, but perfect cubes, pyramids, cylinders, those shapes would suggest intention, design, purpose. Because nature doesn't build corners. Nature smooths edges. Nature rounds everything, given enough mass and time. We've learned something else in our journey, something about thresholds and transitions. We've seen that there's no single sharp line dividing round from irregular planet, from asteroid star, from brown dwarf. Instead, there are gradient zones where outcomes depend on subtle differences in mass composition temperature history. Mimas barely made it to roundness. Vesta almost made it, but didn't quite. Ceres crossed the threshold decisively. Each object tells a different story, holds a different place in the spectrum, from fragment to sphere. Research shows that the universe is full of these in-between states, these threshold objects that remind us that categories are human inventions. Nature doesn't recognize clean boundaries. It creates continuums, gradients, transitions. But through all that complexity, one pattern holds more mass, means more roundness, not linearly. There are exceptions and complications, but generally reliably as a trend that governs structure across 60 orders of magnitude in size. From water droplets 1 millimeter across to superclusters of galaxies, hundreds of millions of light years. In extent, the principle remains. Forces seeking balance create spheres. It seems as though we might have found one of the universe's deepest preferences, one of the shapes it returns to, again and again, like a river finding the sea. As you lie here, now feeling the weight of your body pressing against the mattress, remember what that weight represents. It's gravity, pulling you toward the center of Earth, the same force that shaped this planet into a sphere that holds the moon in orbit, that keeps the sun burning, that creates black holes and clusters, galaxies. You're part of that system, made of atoms forged in stars that were themselves spheres, living on a sphere, looking up at spherical moons and planets, held by a force that has been shaping spheres since the first stars formed 13 billion years ago. There's something deeply connecting about that realization. You're not separate from the cosmos. You're woven into it. The same laws that govern the largest structures also govern your smallest cells. The same forces that shape galaxies also pull you toward sleep. Some believe this might be the final lesson spheres teach, that we're participants in cosmic patterns, not observers outside them. that the architecture of gravity includes us. That roundness, in some sense, is the shape of home at every scale. We began this journey with a simple question. Why does gravity shape the universe into spheres? And the answer unfolded across hours of gentle drift through space and time turns out to be beautifully simple. Because spheres are what happens when you pull equally from all directions. Because they require the least energy to maintain. Because they represent forces in balance compression, meeting resistance at every point, gravity and pressure, negotiating a peace that can last for billions of years, not by magic, not by design, by mathematics working itself out through matter and time. The universe doesn't force spheres on us. It simply makes them the easiest answer to the question, how should I arrange this mass? And that answer echoes everywhere, in raindrops and planets, in stars and black holes, in your eyes, which are spheres that let you see other spheres, in your cells, some of which are spherical, in the bubbles that form when you wash dishes, and the planets that form when nebulae collapse. Spheres everywhere you look once you learn to see them. It seems as though the cosmos might be simpler than we imagined, governed by principles elegant enough to remember patterns, reliable enough to trust. Sleep well in that knowledge tonight. Dream, gently knowing you rest on a sphere that took billions of years to round itself, that's still settling, still adjusting, still participating in the ancient conversation between gravity and matter. The earth holds you. Gravity pulls you softly toward its center. And somewhere above, spheres beyond, counting, drift through darkness, each one proof that the universe knows how to find balance, how to create beauty from simple rules. You are held by geometry, as old as time itself. Thank you for drifting with me through this long, quiet exploration. Thank you for wondering about spheres and gravity and the patient architecture of the cosmos. Thank you for letting curiosity guide you through the darkness. There are more stories waiting in the stillness, more gentle journeys through space and time, more cosmic truths whispered softly enough to carry you toward sleep until we meet again in the quiet spaces between questions and answers, between waking and dreaming, between the stars overhead and the sphere beneath you. Rest well. Dream gently. Good night.